Hey everybody, we're going to begin a little bit of a background study on what the heck calculus actually is. It's a pretty old subject and it's been studied a long time. A lot of people have contributed to this, and I thought we'd kind of break it down so you can see where it comes from. What everyone would agree upon is that there's really two different types of problems that calculus came from. One of them is called the area problem, the other one is the tangent problem. They seem to be completely unrelated, and later on in the year we'll find out that they're very closely related. So today on this movie we're going to be focusing on the area problem, and just for a time frame we're talking 2500 years ago. This is something that most people would give credit to the ancient Greeks on starting the ball rolling on this, and like I said before, tons of people contributed. So let's take a closer look. A good way to think about it is when you first learn the concept of area in general, all the shapes that you see on the screen, like for instance over here we've got square, triangle, rectangle, trapezoid, hexagon, parallelogram, pentagon, circle, and these are some examples of shapes that you can find the area of, and of course you can combine a couple of them together. You could maybe say, hey, I can take this hexagon and put it on here and I can maybe find the area because I know the formula separately. And if you group all these things together, the thing I guess my point is here is that everything that you see here that I'm moving to the left side of the screen, I want to refer to these as Euclidean shapes. There's formulas for everything. They have straight sides. And then you've got this loner over here, the circle. And before people were able to calculate the area of a circle, the only option was to use some other shapes. And for instance, if you take this shape and try to fit it inside there, you can see that the circle may be or the pentagon's an approximation for the circle. So the Greeks, again, were after this idea, and what they were trying to figure out is how do you actually determine the area of a circle? And again, their option was, at the moment, was to find a triangle, fit it inside the circle, and you can see you have this little gap right here. Not so good. So it's a little bit of an underestimation. Increase the number of sides, the underestimation becomes a little smaller, and then that continues on the rest of the shapes to a pentagon, to a hexagon, and you can see this underestimation is getting smaller and smaller and smaller as we go along. So then I quit right here in the octagon. But you can see this is an 8-sided figure, and it's pretty good. So the Greeks said, well, hey, why don't we do this? Instead of thinking it like a finite number of sides in the polygon, why don't we just make it a polygon of an infinite amount of sides? Which leads to the idea of a limit. As the shape reaches its limit, the polygon will eventually turn into a circle with an infinite amount of sides. To take this to the next step, basically what was studied further along in time is the idea of a function of y is equal to x squared. And if I look at the graph of this thing under just kind of a normal zoom, we know what this thing looks like. But one of the questions that came out is what happens if you actually want to find the area underneath this curve? It seems like a pretty strange question, but basically what they're trying to say is, let's say this point is 0, 0, and this point right here is 1, 1. If you look at this region here, bounded by this area, this is the area they're referring to. And the thing I want you to notice is there is no shape we've ever seen that has an area like this. So there's really no known way to do it. And here's how the mathematicians back then figured it out. So here's a zoomed in drawing of y is equal to x squared, represented by the line that you see right here, or the curve. And here's what the Greeks did. They decided that what they could do is split this up into a shape that they would know. What shapes did they choose? They chose rectangles. And so you can see here that this is a bit of what we call an overestimation. It's pretty decent though. And the thing that they knew also is that you could just increase the number of rectangles if you wanted to make it look a little bit better. And I'll do that right now. There's 7, 8, 9, 10, 11, 12. And you can see as I do this, the amount of overestimation is going to continue to get smaller than smaller, and hopefully you're thinking this would be perfect if we could use an infinite amount of rectangles. You can also do it for an underestimate perspective, and you can see here that this little gap between the rectangle and the top of the curve represents an underestimate. which gets better as I increase the number of rectangles. So you can see if I can get to infinity, I'm perfect. You may be thinking to yourself, why the heck would I want to do this? And that's a super legitimate question. You may remember this formula from science. Work is equal to force times distance. So let's imagine that the x-axis is a measurement of distance. The y-axis is a measurement of force. If I multiply this distance on the rectangle, it measures distance. This measures force. If I take force times distance, this area would represent work. And the great thing about it is you can name this whatever variables that you want. When you multiply those two things together, you can make this area represent what you want to do by what variables that you choose. It makes it such a tremendous thing to be able to do. So as you'll see, as we progress through the year, we can estimate it, and we're going to work through calculus to be perfect on how to solve the area problem.